Are you ready?
Sure.
Okay, so let's resume. We're happy to have Clay Cordova from Chicago, who's going to talk about higher group symmetry and applications.
All right, thanks everyone. Thanks to the organizers for giving me this opportunity. Today I'm going to introduce you to this concept of higher group symmetry, which is something that I've been thinking about for the last couple of years, and I'll give you kind of a smorgasbord of applications to various different aspects of quantum field theory. Before getting started, I'd like to just give a shout out to all my great collaborators that I've been lucky to work with over the last 2 years. Here they are. And let me also flash some references. So my starting point in this subject was introduced in the first 2 papers on this list, which came out about 1.5 years ago. And then some of the applications that I'll talk about today are based on these next 2 papers, which will hopefully appear both very soon. And I'd also like to point out some foundational work in this area that was done in papers by Kapustin and Thorngren, and also closely related ideas in the condensed matter literature by Barkeshli, Bonderson, Cheng, and Wang, and also work by Tachikawa. Okay, so what is the big picture? What are we trying to do? So the kind of motivation is that symmetry, that is global symmetry, is one of the few universally applicable tools to constrain quantum field theories and their dynamics. And what we would like to do is to explore symmetry, generally speaking. So what symmetry principles exist, and we'd like to kind of go deep down and understand how these can be used to constrain dynamics of quantum field theories. So one important new development in this area in the last few years has been generalized global symmetry. So this is a powerful new organizing principle. And what's generalized about it? Well, we have, in this terminology, we have ordinary, that is zero form global symmetries, and these act on local operators, and everybody's familiar with these. And then we also have higher form global symmetries, and these are characterized by their actions on extended defects. And the kind of big picture of this talk is we'd like to understand what possible mixings can occur when we have both types of symmetries, that is ordinary global symmetry and higher form global symmetry. And you could think that this is sort of an analog of looking for non-abelian structures in these symmetries. And what we'll see is that higher group global symmetry is one general possibility for mixing of form symmetries of different degrees. And I'll introduce this concept and then apply it to a bunch of different seemingly disparate questions. Okay, so let's get started with some more technical details. So a continuous Q-form global symmetry is characterized by the existence of a Q+1 form conserved current. We'll call it J superscript Q+1. It has Q+1 indices. It is totally antisymmetric, and it is conserved. The currents are a good way to characterize continuous global symmetry. Of course, all of these concepts also exist for discrete global symmetry, where the currents aren't as useful, and then we'll have to invent a new perspective, which we'll talk about a little bit later. The charged objects under a Q-form global symmetry are extended operators of dimension Q. So for Q equals 0, that's the case of ordinary global symmetry. These are point operators. For Q equals 1, these are line operators. And for Q equals 2, these are surface operators. And if you've never seen this before, it might seem very abstract, but a basic example to sort of latch onto and make everything feel quite concrete is 4D abelian gauge theory. That is just free Maxwell theory. In this theory, we have the Bianchi identity and the free equation of motion, and these imply both that F is conserved and that star F is conserved. So F here is the field strength. And so by this definition on this page, we conclude that Maxwell theory has one form global symmetry, which is U1 times U1. So what are the charged operators under these symmetries? The charged operators are Wilson and 't Hooft lines. And to say that an operator is charged means that if you have a two-sphere that links a line L, and you put this integral of this current on the 2-sphere, then you can unlink the sphere on the line at the expense of a phase, which you think of as the charge of the line. So here's the geometry in pictures. We have the red 2-sphere. It's linked with the blue line. We can unlink them and collapse the sphere and remove the insertion of the integral of the current at the expense of a phase. And in Maxwell theory, this is true by Gauss's laws. Okay, now we've talked about currents. In general, when you're studying global symmetry, it's also useful to couple to background gauge fields. And this leads to a partition function. The partition function is a function of the background gauge field. So I'll call the background gauge field sometimes A, and Z will be a function of big A. And in this discussion, it's important to remember that A is a fixed classical source. And for a continuous symmetry, Z of A is a generating function of correlation functions for the current J. So at least a first approximation, that's how you think of the partition function. Now, higher form global symmetry currents naturally couple to gauge fields with more indices. So for instance, a 1-form symmetry couples to a 2-form current B. Just in the standard way, B contracts with the indices of J. And now current conservation means that the partition function Z of B, which we think of as a function of this background 2-form gauge field, is invariant under gauge transformations with a 1-form gauge parameter, lambda 1. And of course, like other notions of symmetry, this invariance could be violated by 't Hooft anomalies. Okay, so we've done a little warm up. We've talked about ordinary global symmetry a little bit. We've introduced 1-form symmetry. And now we could ask a kind of innocuous question. Let's take simple interacting theory, 4D QED. So we have a U1 gauge theory with NF fermions of charge Q. And we can ask, what is the symmetry of this quantum field theory? This is a basic question that we hope to be able to answer. Well, there are certain pieces of it that are obvious. So first of all, there's the SUNF left times SUNF right ordinary global symmetry that acts on the left and right-handed Weyl fermions. And finally, well, in addition, there's also this, there's also 1-form symmetry. We mentioned previously that Maxwell theory had U1 times U1 1-form symmetry. Here, one of those currents is gone because of the charged matter. F is no longer conserved, but star F is conserved by the Bianchi identity. So there's still a U1 1-form symmetry, which we can think of as measuring magnetic charge. So we have this U1 1-form symmetry, and we've got this non-abelian ordinary global symmetry. And naively, you might expect that these things don't talk to each other, but in fact, they mix. And this mixing is basically the key thing that we want to zoom in on in the rest of the talk. So one way to diagnose the mixing and this interesting behavior is to examine a triangle diagram. So in this case, it will be a triangle diagram with where the legs are 2 flavor current insertions, that is the ordinary global symmetry flavor current insertions, and an insertion of a dynamical gauge field. Now I remind you that triangle diagrams, like we study in QFT textbooks, have various different interpretations depending on whether the vertices couple dynamical gauge fields or current for flavor symmetries. So let's just quickly go through them. So perhaps the most familiar one is the one where all 3 vertices are dynamical gauge fields. This is often called the gauge anomaly. And this must vanish if the theory is going to be mathematically consistent. The next is where we have 2 gauge vertices and 1 flavor vertices. And this is sometimes called the ABJ anomaly. And if it's non-zero, it means that the flavor symmetry is broken. Another much discussed triangle diagram in recent times is flavor cubed anomalies. These are 't Hooft anomalies. They mean the flavor symmetry is unbroken, but these have the important implication that they match along RG flows and constraint dynamics. And finally, we come to the situation that we're discussing here, where we have 2 flavor insertions and 1 gauge insertion. This means that the flavor symmetry is unbroken, and what we will see is that the implication of this kind of triangle diagram is that it deforms the current algebra between the flavor symmetry and the 1-form symmetry. And it's this deformed current algebra that we're defining as higher group global symmetry. So in this case, it's called a 2-group. the higher group is called a 2 group because the highest form current involved has 2 indices. And this also matches with some previous existing mathematics literature about this subject. Okay, so I advertise that there's some current algebra. Let's get a little bit more explicit about what it is. So the mixing between the ordinary 0-form global symmetry and the 1-form global symmetry in this example is encoded in a 3-point function where we have 2 ordinary global symmetry currents and 1-form global symmetry current. That's this 3-point function here. And you should think that looking at this 3-point function is analogous to what you do when you look for at the 3-point function of ordinary global symmetries to find the non-abelian structure constants. So here we're doing something quite similar. So what do we have? Precisely we have ward identities relating this 3-point function to the 2-point function here of 2 1-form global symmetries. It's easiest to state these ward identities on a special locus in momentum space where p squared is q squared is p plus q squared. So the 2-point function is easy to constrain. There is some tensor structure here. There's some tensor structure that's completely determined by conservation. I won't write it. And then there's a structure function f of p squared over m squared, where m is some scale. And the ward identity that we were talking about relates that same structure function to a particular structure in the 3-point function. So in this 3-point function, we have some other tensor here. We have some to contract some group theory indices. We have the same f of p squared over m squared, the same structure function. And then we have a very important coefficient kappa that we'll discuss a little bit more below. And QED, 4D QED, realizes these identities with kappa equal to Q, the charge of the fermions, and the currents given by what we discussed before. So you can also think of these ward identities as being a consequence of certain important contact terms in the operator product expansion of 2 ordinary currents. So we could take the divergence of an ordinary current and collide it with another current. Now, the ordinary global symmetry is a symmetry of this problem. So the divergence of that current is 0 at separated points. So when we collide it with another operator, we can at most expect to find a contact term. And there is one very natural contact term that you can find, which I've written here. So it has the 1-form global symmetry current appearing on the right-hand side, some derivative of a delta function, and then again this structure constant kappa. And we're going to see that this structure constant kappa is something analogous to like FABC and a Lie algebra. It's what's specifying the deformation of the current algebra. Now let me remind you that you may be familiar with these kind of contact terms in the OPE of a current, and they're typically associated with charged operators. So usually you have the divergence of the current hits a local operator and returns something proportional to the charge of that operator. And in the operator product expansion that I mentioned above related to the higher group, there's a derivative on the delta function. And this means that the global charge algebra is not modified, even though the current algebra is deformed. So these ward identities and OPEs give us one way to think about what this deformed current algebra, this higher group symmetry is. But there's also another way, which is background fields. So if we have both an ordinary global symmetry and a 1-form global symmetry, for instance, the appropriate background fields are, at least locally, a 1-form gauge field A and a 2-form gauge field big B. And if we have this higher group symmetry structure, these now mix under gauge transformations. So here, A, the ordinary global symmetry background field, has a standard gauge transformation. The first part of the transformation for the 1-form symmetry background looks standard, but now there's a new piece. So this constant kappa appears, and also the gauge parameter small lambda appears, and the gauge field small a, big A appears. And if you're thinking, gee, this formula looks familiar, you're right. What this is a Green-Short's transformation for background fields. So usually when you think about the Green-Schwarz mechanism, you have in mind some kind of some dynamical B field, which has the kind of interesting gauge transformation rule that's cooked up to cancel some important anomaly. And here we have something similar, but actually logically prior. We have the situation where those dynamical fields are not yet, those fields, that B field is not yet dynamical, but is rather background. And so the important point is that if you have this kind of global symmetry, this higher group global symmetry, the modified transformations above make the partition function Z, which is now a function of both capital A and capital B, they make it invariant, of course, up to C number anomalies. Okay, so what's in this name, higher group? Well, for instance, in mathematics, this pair A1, B2, together with the gluing rule specified by the gauge transformations, is called a two connection on a two group bundle. That's one place where we got this name. And one important general feature is that this structure constant kappa must be quantized in integer units. How do we see that? Well, one way to see it is to look again at this Green-Schwarz transformation for B. And here what you see is something kind of funny. You see that a naked gauge parameter lambda appears. Usually when you see gauge parameters, they occur with derivatives. And there's a good reason they occur with derivatives is because the gauge parameters are ambiguous. When you go around to one cycle, little lambda could shift by 2 pi times an integer. So this formula here looks a bit suspect because of that. But in fact, all is well. If kappa is an integer, then that ambiguity can be compensated for by a gauge transformation involving big lambda 1. So that's why we need kappa to be integer quantized. And let me just briefly comment that when you generalize this kind of structure from the simple example that I'm giving here to ordinary, discrete zero form groups G and other discrete one form groups K, you find again an analog of this, this structure kappa, and you find that it's some element of a group cohomology class. Some element of group cohomology. Okay, so I've introduced this concept of higher group symmetry, and once you get here, you find that higher group symmetry is in many ways similar to ordinary global symmetry. So what do I mean? I mean that first of all, various groups are possible. The zero form symmetry can be abelian and non-abelian. Both the zero form and higher form symmetry could be discrete. This higher group global symmetry could be emergent. It could pop out along an RG flow. It can be spontaneously broken. And it can also have 't Hooft anomalies, which have their own universe of classification and match along RG flows and constrained dynamics. And so in the rest of the talk, I'd like to take this concept of higher group symmetry and apply it to a couple different cases and show you a little more. So the first thing I'd like to tell you about is how do you think about this notion when the symmetries are, say, discrete and you don't have currents? So this was a subject of a paper that I wrote with Benini and Sin. So the way to proceed here is that you characterize the global symmetry in these examples in terms of symmetry defects. So symmetry defects are very useful objects for thinking about discrete symmetries because you don't have currents. So what are the rules? So there are kind of there are various important rules. So first of all, the zero form symmetry defect is a codimension 1 object. A 1 form symmetry defect is a codimension 2 object in your theory, and so forth. And what are the rules? Here they are. So if you take an operator phi and you move it across a symmetry defect labeled by some group element G, then you implement the group transformation G times phi. The defects are topological. So if you deform the shape of the defect, it stays the same. That's supposed to replace the notion of current conservation. And finally, why do they form a group? Well, the group is encoded in the fusion law. So if you have a defect G and a defect H and you collide them, you'll get a defect for the composite group element. Okay, so these symmetry defects give you actually a way to encode higher group global symmetry just abstractly in terms of the fusion algebra of these defects. So let me explain it to you in the case of a 2 group. The case of a higher group is quite similar. So let's let G be the 0 form symmetry and A the 1 form symmetry. And then if you have a quantum field theory that occurs in 3 space-time dimensions and above, you cannot avoid the situation where 3 global symmetry defects intersect. So here I've drawn a picture where 3 global zero-form symmetry defects intersect. So we have G, we have H, and we have K. Their pairwise intersections are shown in red. And their codimension 3 triple intersection is shown at this black dot. And what can happen is that at that black dot, a one-form global symmetry defect can emerge. This is shown in blue. And this emergence, this possible fusion algebra is characterized, in fact, by a group cohomology class in H3 of G with coefficients in A. And that is what how you think about abstractly this higher group in this case. Okay, so this is not just a purely kind of abstract nonsense discussion. It actually has some explicit consequences, both in 3D Chern-Simons matter theories and in 3D TQFTs. So this has been somewhat discussed in the condensed matter literature. For instance, in 3D TQFTs, these are characterized by a modular tensor category. And the most natural setup where this the situation that I was talking about occurs is that you have G, the zero form global symmetry, is the automorphism of this modular tensor category, and A, the one form symmetry, are the abelian anyons of the theory. And then the action of G on A actually encodes typically a 2-group global symmetry. So this is a ubiquitous phenomenon in topological quantum field theories. Okay, so I've now given you some discrete examples of higher groups and explained how to think about them. And now I'd like to move on to a different topic and a different application of this notion. And this new application is some constraints on emergent symmetry that you can derive using higher group global symmetry. So let's suppose we have the very general situation where we have a renormalization group flow where the ultraviolet does not have a higher group global symmetry, but the infrared does. Now in this situation, we can think that there's an energy scale EQ below which the Q form symmetry is effectively respected. So it's difficult to define EQ exactly, but we can certainly talk about scales far above EQ where the symmetry is gone and scales far below EQ where the symmetry is present in the effective field theory. And one way to think about this is that in the EFT that's applicable below the scale EQ, there are Q-dimensional defects charged under the emergent symmetry. And at the scale EQ, these defects become the world volumes of new dynamical degrees of freedom. So for instance, if we are talking about a 2-form global symmetry, which we will be momentarily, there are charged surface operators at long distances, and at the scale E2, you could resolve these, the thickness of these objects, and you could think of them as the world volume of dynamical strings. And it's the fluctuations of these dynamical strings that destroy the symmetry, this 2-form symmetry above this scale E2. Okay, so now suppose you have this situation, but you're talking about a higher group symmetry, i.e. a non-zero value of this structure constant kappa. Then what you can show is that in this situation, the scales EQ obey a very general inequality, E0 less than or equal to E1, less than or equal to E2, etc. How can we understand this? Well, one way to understand this is by examining the transformation rules for the background fields. So for instance, let's return to the example that we introduced explicitly, this 2-group transformations. What do you see? You see that because of this Green-Schwarz term, the gauge transformations of the ordinary gauge field A activate the background field B of the 1-form symmetry. Therefore, if the 0-form symmetry is present and you can couple to A, the 1-form symmetry must also be present so that you can couple to B. So that's an instance of this kind of inequality, E0 less than or equal to E1. And by generalizing this argument, you can argue for this nested sequence of inequalities in general. So it turns out that axions provide a kind of cute set of examples to illustrate these constraints on emergent symmetry. So what's an axion for my purposes? For my purposes, an axion is a periodic scalar field A with some periodicity 2 pi f. And all such theories have an interesting two-form global symmetry with current J3 ABC that is star dA. And the charged objects are surfaces, surface defects, with the feature that as you integrate dA around them, you get a multiple of the periodicity, where the integer multiple n appearing there is the charge of the defect. Okay, so what's the scale E2 in this situation? The scale E2 is where the two-form symmetry is broken, and we expect some new fields in this effective field theory. For instance, A may become the angular part of a complex scalar phi, where the radial part of phi is liberated at the scale E2. That would be one possibility. And parametrically, you expect that E2 scales like F, but these, of course, may differ by some dimensionless couplings. Okay, so the key point is that in models where axions couple to non-abelian gauge fields, there is in fact a higher group global symmetry. So let's consider a very standard Axion-Yang-Mills Lagrangian. So we've got some gauge kinetic term for some SUN gauge fields. We've got a kinetic term for our axion field. And then A couples to the instanton density as A trace F wedge F. And the scale F appears in the denominator. Okay, so the axion has the two-form symmetry that we discussed before, but the SUN gauge fields themselves also have an interesting higher form symmetry. They have a ZN one-form symmetry, a discrete one-form symmetry. And this ZN one-form symmetry, what does it act on? Well, it measures the charges of Wilson lines. So in this example, there's no dynamical fundamental matter. There's only adjoint matter. So Wilson lines in the fundamental cannot be screened. And that gives us this ZN one-form symmetry as a good quantum number. Okay, so then given that there's this higher group as demonstrated in these two papers here, we would deduce from our previous discussion a very general inequality on any UV completion of this model, which is that E1 that is less than or equal to E2. So what are these scales? Well, we mentioned that E2 is the scale where the strings become dynamical. And what is E1? E1 is the scale associated to the one-form symmetry. That's where charged fundamental matter appears. Okay, so let's see how this is enforced in a explicit concrete example. So we could look at a Kim, Schiffman, Weinstein, Zakharov axion model. And this arises from an action of a very standard form. So here we have a gauge kinetic term. We have some fundamental fermions psi. They're in the fundamental of SUN. And then there's also a neutral scalar phi. Phi couples to these fermions with a Yukawa coupling. And then there's also a kind of Mexican hat type potential with quartic coupling M. Okay, so if you just quickly analyze this model, what you find is that, well, the minimum of the absolute value of phi is at F, at least superficially. And then plugging in and turning the crank, you would find that this model leads to Axion-Yang-Mills at long distances, where, because of a Pecha-Quinn type mechanism, where A becomes the angular part of phi, and the decay constant is F. Okay, so then you could look at this model and you could examine this constraint that we had derived before, E1 less than or equal to E2. And what you would conclude is that if you want Axion-Yang-Mills to really be the effective field theory, then you need lambda, the Yukawa coupling, to be less than or equal to M, at least parametrically, the quartic coupling. So that's by comparing the scales at which the fermions come back and the scales at which the radial part of phi comes back. So how is this enforced? So there are a couple ways you could try to violate it. So one way is you could just try to go to strong coupling. Of course, then I can't say anything. But it's actually more illuminating to see what happens if you try to violate this inequality at weak coupling. So we could take both lambda and M, both the Yukawa and the quartic coupling, to be tiny, but take them to be in the reverse hierarchy. So the Yukawa coupling much greater than the quartic. And then what you find is that there is a quartic, there is a one loop contribution to the potential for the radial mode. So this one loop contribution moves the minimum of the potential from F to above the UV cutoff. So it moves lambda, it moves the minimum of the radial mode to big lambda, the UV cutoff, divided by small lambda. And so what this means is that at low energies, the angular mode A is effectively non-compact, right? The periodicity of A has become larger than the UV cutoff of your theory. And so this thing no longer interacts with the gluons. So this is basically illustrating this inequality. If we want to have the K NSVZ model flow to Axion Yang-Mills, we need this inequality on the Yukawa and the quartic. Okay, so that's the end of this topic. The final topic where I'll apply higher group global symmetry is to 6-dimensional quantum field theories. And this is the subject of some upcoming work with Dumitrescu and Intriligator, building on a series of works by us in this subject. So what's the basic paradigm of these quantum field theories? So 6D SCFTs and little string theories, well, they have the feature that at long distances, they tip on their moduli space, they look like gauge theories, often non-abelian gauge theories. And the fixed point that one is interested in talking about is in the ultraviolet. And by now, many, maybe even all, examples of this SCFTs and little string theories have been constructed in F theory in a sequence of papers by Vafa, Heckman, and many others. Also, Rodelius and Morrison's name should be in there. Okay, so why am I talking about these? Well, in the infrared effective field theory, there's of these models, there is always an interesting one-form global symmetry. What is it? So you take trace F wedge F for the non-abelian gauge field, take star of it, and that gives you a two-form conserved current. This is present ubiquitously. So we could ask, are these one-form global symmetries also present in the ultraviolet fixed point, whether it be a SCFT or a little string theory, and do they form any interesting higher group structure? So we'll see that there's a kind of bifurcation depending on whether the ultraviolet is a superconformal fixed point or a little string theory. So let's discuss the first case where the UV is a conformal fixed point. So in this case, there are dynamical tensor multiplets that are crucial. And these have bosonic fields, which are a real scalar that I call rho, and a dynamical fluctuating two-form gauge field small b. Small b should not be confused with big B. The action necessarily includes couplings of the following form. Rho times the kinetic term for F squared. So why is that one necessarily there? Well, it's because without that, the gauge kinetic term would break conformal invariance. So by making the coupling dynamical, that is by having rho multiply the kinetic term, you can try to restore conformal invariance. And then crucially, that coupling has a super partner, which is this small b coupling to J, this instanton current. So when you look at this action, what you see is that the one-form symmetry that we were talking about is in fact gauged. It couples to a dynamical gauge field. And so we expect that it disappears in the ultraviolet superconformal field theory. We expect there is no one-form symmetry there because of this coupling. And in fact, this is the case and could be demonstrated in a completely different abstract way. Simply look at the unitary representations of the appropriate superconformal group in 6 dimensions. And what you find is there are no unitary representations that can contain this one-form global symmetry current. So there are no such currents at all in any 6D SCFT. There's no one-form global symmetry. And then, of course, because of that, there are no continuous higher groups. So that's the situation for conformal field theories. And the way I phrased it just now, it sounds like a negative result. There's no higher form global symmetry. And and there's no or continuous one-form symmetry, and there's no higher group symmetry. But this negative result actually has some important implications. So recall that from our previous discussion that we could fix the higher group structure constants by examining mixed anomaly terms involving flavor or asymmetry gauge fields, background gauge fields, and dynamical gauge fields. So what we learned from this discussion is that the mixed anomaly coefficients, those that would imply a non-zero higher group structure, non-trivial higher group structure, must in fact all vanish in any superconformal field theory. So that's what I've written here. We have 0 equals the mixed total anomaly. Now this mixed total anomaly, if you're working on the moduli space, it looks like it splits into two pieces. One is easy to determine. This is the contribution from the matter fields that you just get by looking at the various representations, gauge groups, etc. And then there's another that's harder to figure out. It's how it comes from how the dynamical B fields couple to these background gauge fields. These are the Green-Schwarz contributions. And so a priori, you might not know what fixes these Green-Schwarz contributions. But in fact, by this equation, because the left-hand side is known to be 0, the right-hand side is also, and this term is fixed, this mixed contribution is also fixed. So to summarize, what does that mean? It means that all 't Hooft anomalies of the ultraviolet superconformal field theory are fixed completely by the IR moduli space gauge theory description. And this matches very nicely with an earlier proposal by Omori, Shimizu, Tachikawa, and Yonekura.
You have 5 minutes, Clay.
So we can also use our new knowledge about the 't Hooft anomalies to prove some other general results about 60 SCFTs. So for instance, using supersymmetry, we can determine all of the conformal anomalies of 60 SCFTs purely from their IR moduli space, because supersymmetry relates the 't Hooft anomalies to the conformal anomalies. So this means, for instance, that the 2 and 3 point functions of the energy momentum tensor at the fixed point are completely determined just from the moduli space matter content. We can also learn something interesting about the A-type conformal anomaly. This A-type conformal anomaly features in the A theorem, which is of course still partly conjectural in 6 dimensions. But what we can show using our method, our moduli space method for computing A, is that we can show that for all 60 SCFTs, A is necessarily non-negative. And this dovetails very nicely with the idea that A is a kind of measure of the degrees of freedom of a superconformal fixed point. Okay, so that's everything I wanted to say about SCFTs. Let me make some final comments about little string theories and how higher group symmetry is prominent there. So let's consider, for example, the type 2b 1,1 little string theory. This arises from the decoupling limit of NS5 branes. And in this case, the low energy effective field theory is super Yang-Mills with gauge group SUN, where N is the number of branes. And we can look at this instanton current. Oops, there's a typo. It should read J2 is star trace F wedge F. And this measures the fundamental string charge. So in fact, because it measures the fundamental string charge, which we know to be a good quantum number in string theory, we expect it to be present along the entire RG flow. And in particular, the background B field that we've harped on so much, the background field for the one-form symmetry, this has a very physical interpretation in this example. It's simply the decoupled NS sector B field from type 2b string theory. So we expect this one-form symmetry to be present in the little string theory. And these theories, of course, also have SU2 times SU2R symmetry. And it's natural to ask whether these symmetries are assembled into a higher group. And the answer, of course, is yes. Otherwise, I wouldn't be telling you. So since there's no tensors, no dynamical tensors in this example, there's no Green-Schwarz couplings to worry about. And we can read off the structure constants of the higher group from box diagrams involving the infrared gauge fields. So these are box diagrams which have 2 flavor insertions and 2 gauge insertions. And in this case, you find terms of the form I8 mixed Well, there's a second Chern class of the dynamical gauge field C2 of F. Then it's multiplied by a difference of second Chern classes for the two R symmetries, R1 and R2, and then you have N, that number of branes appearing there. And so because this is non-zero, we have a non-trivial higher group in this little string theory. And we have all of its ensuing ward identities that I discussed before, which are relations on momentum space correlators for the little string theory. So it would be interesting to think more about those. And this appears to be ubiquitous, this presence of higher group symmetry in little string theory. So for instance, just to throw out one other example, the SO32 small instantons have a rich higher group structure involving both the flavor, Lorentz, and one-form symmetry, all of which are mixed together, and there are lots of ward identities there. Okay, so I've finished. Let me conclude and highlight a couple interesting open directions. So I hope I've convinced you that higher group global symmetry plays a prominent role in many quantum field theories. These include three-dimensional Chern-Simons matter theories and topological field theories, 4D gauge theories, models of axions, superconformal fixed points in D greater than 4, and probably many others that I didn't even think about. And higher group global symmetry may also be a useful tool to organize little string theories, maybe into something like universality classes. Now, there are many open directions to explore, and many other people are working on related topics, but let me just highlight two that I thought are particularly interesting that I didn't get to talk about. So one is that we talked about higher group global symmetry as a global symmetry, where you have just background fields. But it's quite interesting to promote these background fields to be dynamical. And this is especially useful in the case of discrete symmetries. This leads to a very interesting, rich class of topological field theories that has recently been explored, for instance, by Thorngren. And finally, let me also mention some work in progress, is that in 4 dimensions, there's a close connection between two-group global symmetry and some aspects of the Kalland-Rubakov effect. And I hope to have an opportunity to tell you about that in the future. Thanks very much.
Let's thank Clay for that very nice talk. Questions, Nathan Cyber?
Yes, so regarding the little string theory, it doesn't really have meaningful local operators. So how do you think of the objects that participate in the...
Yeah, excellent question. So my understanding is that it doesn't have local operators, but it does have momentum space, suitably smeared momentum space correlation functions. So those are some class of good observables. So I think that these ward identities in momentum space, smeared versions of them still have interesting implications. But let me stay on that kind of safe ground.
So the danger, of course, is that if you try to take these momentum modes and reassemble them into coordinate space operators, then...
Yes, that is not supposed to work. So...
well, it doesn't work because different components get different renormalization.
Yeah.
So I'm not quite sure what will happen. So are you going to do everything only in momentum space, or what do you have in mind?
Well, I certainly have in mind that in momentum space, the ward identities that we wrote down at the beginning still apply to little string theory. But if you ask me to pin down what are the complete list of meaningful momentum space observables that you're allowed to study, that I don't know the answer to. I think maybe some experts in little string theory do, though.
So I have a variant of this question. What are the charged objects under this symmetry, especially in the context of the little string theory?
That's a good question. So so I don't know the physical description of the answer in little string theory, but I think that's somewhat related to the second open direction work that is being discussed here. So I think the right answer, which we're working on, is ray operators. So it's not like a line that ends at a point. And that smells like the right answer because the line might be able to talk to the one form symmetry, and the point might be able to talk to the zero form symmetry. And so if you can look at some kind of rays together, maybe with some, or maybe even junctions between like operators that live on the line, those are the right notions of charged objects. But that's sort of the subject of this second work in progress.
And should these be meaningful in the context of little string theory?
Well, that would be very interesting if the answer is yes. Yeah, I think, I mean, you know, that one form symmetry, when it acts on the vacuum, I guess you could think that it makes a little string. So, so this is like, would be some kind of domain wall in the little string. That's a good, yeah, I haven't thought about it too much beyond that.
Okay, Yifan Wang.
Hi, Clay. Nice talk. So I have a follow-up question about little string.
Okay.
So many of this little string theory, I mean, whether it's 1, 0, 2, 0 supersymmetry or 1, 1, they have a holographic description in either type 2P or heterotic string. So do you know how this two-group structure will show up on the worldsheet in the worldsheet description?
In the worldsheet, no, I'm not sure. That's an interesting question.
So have you already determined this two group for, you know, say the 2, 0, 1, 1 type little string theories?
Yeah. So for instance, here, this was from this formula here, you can read off what it is in the 1, 1 type 2B little string.
I see.
Yeah. We haven't explored in complete generality. Just a few examples to note that it's sort of all over the place. I mean, once there's no theorem forbidding it, then you should expect it. I mean, that's kind of the general mantra in this higher group global symmetry in general, is that if you have zero form symmetry and higher form symmetry, or if you have form symmetries of different degrees, unless you have some specific reason to expect that they factorize, they typically form a higher group.
I see.
Davide Gallotto has a question.
Hi. So you mentioned the one form symmetry structure involving the Lorentz group. Is this something that can happen?
So what I mean is that the ordinary global symmetry is the analog of the zero form symmetry in the higher group is being played by Lorentz symmetry.
Is this something that can happen in a local theory, or is it special to?
No, it can happen. It can happen in a local theory. It can even.
Did we lose Clay? Clay, we lost you. Seems like we lost the speaker. Okay, I guess we should end it there. Chef, can you see the local organizers? Can you see what's wrong?
I can't. I don't see Clay on the list of participants right now.
Okay.
Yeah, I think we might have lost.
Perhaps some of his collaborators who are around could answer questions.
Yeah, that's a good idea. Do we have any more questions?
No, Davide was asking, I mean, Clay was answering Davide.
Hello, hello.
Ken is
Hello.
here?
Yeah.
Hello.
Yeah, I guess Clay was talking about the contribution from gravitational anomalies that can.
Hello, 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 hello. Hello.
Hello, I seem to have
Oh,
disappeared from planet Earth for briefly.
good.
I'm not sure why, but am I back to being host? I can go back to sharing the screen. Sorry about that. I don't know what happened.
You should be able to share your screen anyway.
Okay, got it. Davide, are you still there?
Yes.
Oh, you're here. Okay, so I was giving you an example answer to your question, which was about an example of a higher group involving the Lorentz symmetry, the Poincaré symmetry, and some one-form symmetry. So a cute example is to consider U1 gauge theory in 4 dimensions. And you consider 4 fermions with charges 3, 4, 5, and -6. Now this theory is consistent because of this cute equation, 3 cubed plus 4 cubed plus 5 cubed is 6 cubed. So the U1 gauge anomaly is 0. There's a one-form symmetry, again, associated to the current star F, the magnetic one. And now the B field transforms under local Lorentz transformations. The reason is that the sum of these charges, 3, 4, 5, and -6, is not 0. So the sum of the charges is exactly what occurs in a triangle diagram where you have 2 stress tensor insertions and 1 gauge field insertion. So this gives an example where the higher group is mixed. Not sure who's drawing on my screen. That's interesting. With the Poincaré symmetry.
Okay, Davide,
I
are you
see.
happy?
Thank you.
And Yifan, you have another question?
Yes, if I may.
Yes.
So Clay, I have another question. So as you know, the theory on the 2,0 tensor branch has different UV completions, either by the 2,0 superconformal field theory,
Yep.
or by the 2,0 little string theory. The 2 UV completions differ by certain higher derivative couplings.
Yes.
I was wondering if this 2-group structure that you find can help you to constrain what kind of higher derivative terms there should be there.
Ah, that's a nice question. Yeah, that's a nice question. But it
For
sounds
example,
like
as
I
you know,
haven't.
the trace f to the 4th is absent in one case, but
Yeah.
present in the other.
Yeah, I mean, it sounds like there might be something there. I haven't thought about that before, but yeah, you might wonder if the trace f to the 4th being there or not can break the ward identities that I was talking about.
Right.
And I'm not sure. That's a good question. Yeah.
Okay, thank you.
Any other question? Yes, Gurulashmi Subramanian.
Hi, thanks for the nice talk. So I was just curious to know, like, so when we just promote these global symmetries to dynamical fields, do we still get, so for example, the mixed anomaly term generated by the Green-Schwarz, that term, is that still, that cannot be fixed, right? For the dynamical fields?
It's not something to be fixed or not. It's not a bug, it's just a feature. So, if you promote A and B to be dynamical, then you want to sum over A's and B's modulo gauge transformations. You want to sum over them modulo these gauge transformations. Just like when you have an ordinary symmetry and you promote A to be dynamical, you want to sum over A modulo this ordinary gauge transformation.
I see. Okay.
Any other question? Okay, if not, let's thank Clay again. Clap.
Yeah.
And all the speakers of today. And Jeff, I don't know if you want to announce again the public talk.
Yeah. So thank you, Mariana, for the chairing, and thank you for the speakers. Thank you to the speakers for today. So just a reminder that in just a little over an hour, Shamit Kachru will be giving a public talk. Let me display again the advert for the talk for anyone who wants it. So here's the ad for the talk. You can register on Zoom because it's a public talk. We thought we'd open the registration via Zoom and not via this conference. So to register, just go to strings2020.com/public talk, and you'll get an email confirming your registration and with the Zoom link to link to, or I will turn the live stream off shortly, and then we'll turn it back on again for the talk. So the link for the live stream is the same as usual. So we'll have a about an hour break, and for those of you who are joining us for the public talk, we'll see you again in an hour.